Hello everyone. So welcome to the week 7th of the tutorial session of the course Introduction to Robotics. So today we'll solve some questions based on the practice assignments of the week 7th. We'll start the session now, and also this video will be uploaded on YouTube. So the one who missed now can watch it later, and the link will be provided in the NPTEL portal. So the first question is, the angular interval over which the waveform of induced EMF in a BLDC motor remains flat-topped over a cycle is. So, as we have studied, uh, so for 120 degree, as the EMF versus time plot for the three-phase winding system has been given. In this, what we have studied that for 120 degree, the induced EMF will be remains flat topped over a one complete cycle. So this is the interval of 30 degree, 60 degree, like this, 90, 90, 120, 150, and this is 180 degree. Then again this is 360 degree. So over a one period, we can see that the flat topped over one cycle, that is of 360 degree. So it is around 150 minus 30 degree, that is equal to 120 degree. And also this also lies in a complete one cycle. So one cycle is from 0 to 360 degree. So again 120 degree. So the answer will be the waveform of induced EMF will be remain flat topped over a over 240 degree in a complete one cycle of 360 degree. So the answer is 120 degree plus 120 degree is equal to 240 degree. So the correct answer for this question one is option B. So we'll move on to the next question. So among the following statements made about the geometry of a brushless DC motor, pick out the wrong one. So we have to pick out the wrong statements. First, we'll see which statements are correct. So we know that the field generated in the BLDC motor is brushless DC motor is rotating along with the rotor, because with the rotor we have, this is a magnet, and let's suppose this is south pole, this is north pole, and this is also south pole, this is north. So when rotor rotates, then this magnet will also rotate with the rotor. So therefore the field generated, that is the field generated is from in this direction, and it is coming into this direction. So the field generated will also rotate along with the rotor. So this option is the correct option. And the armature conductors are powered without the needs for brushes. So in brushless motor, there is no need for the brushes for the conductors to get power. So option C and option D is the correct. This two is the wrong. So in this question, it is asking the wrong one. So this is the wrong one. So these two options are the answer for this question. Okay. So we'll see the third question. Like in this question, it is given the magnitude of the flat portion and the frequency of the induced EMF in a brushless DC motor while the rotor rotates at a certain speed are E1 and F1 respectively. So the frequency is given F1 and E1 is the EMF. Now, if the speed of the rotation of the rotor is double, then the magnitude of the flat portion and frequency of uh, induced EMF respectively become. So it is asking, as taught in the lecture, we know that magnitude and frequency is depends on the speed of the rotors. So in the first case, E1 comma F1 is the amplitude and the frequency, Now the speed of the rotation is twice. Speed of rotation is two times. Then E1 and F1 will also become the 2E1 and 2F1. So the correct option is option D for this question. So now we will see the question number 4. So this question is the resistance of each phase winding of a brushless DC motor is 0.6 ohm. So in this question, R is given as 0.6. The magnitude of the flat portion of the induced EMF in each phase EB of the machine is given as EB is equal to 0.2 omega. Omega is the speed of rotor in radian per second, and also omega is 60 radian per second. So EB is equal to 0.2 into 60, that is equal to 12. And the DC input voltage to the inverter is given, that is VG is equal to 100 volt. In every 60-degree interval, the respective active switches of the inverter are operated at a duty ratio of 0.75. Determine the average value of armature current following through the phase winding in this case. So here D is given as 0.75. So for H bridge, we know that VA by VG is equal to 2D minus 1. So in this case, our armature voltage will be VG is given 100 and 2 into 0.75 is 1.5 minus 1. It is equal to 0.5 into 100. It will become 50 volt. Now VA is equal to 2 into IARA plus EB. So here our IA we have to find. RA is given 0.6 ohm and EB we have already found as 12. So now and we can write as BA is 50. 50 is equal to 1.2 IA plus 24. So we will get IA is equal to 26 by 1.2. So it will become 2.17, sorry, 21 point. This, if we remove this decimal, 260 by 12, so that will be 2.2 and 20 is 1.80680 again 6 like this. So the armature current following through the phase winding in this case is 21.66 ampere for this question. Now this is a multiple select question. In this question it is asking for an inverter driving a brushless DC motor, which options are the correct? So each switch conducts for a total angular duration of 120 degree. Yeah, this is the correct. There will be one leg with both switches turned off at any given instant. So this is also correct. The switching instant of each switch is completely decided based on the Hall switch information. This is not correct. And there are two switches active in every 60 degree. As in every 60 degree, two switches are active. So option A, C, and D are the correct option for this question. Coming to the next question, that is from the following statements made about Hall effect switches, identify the wrong ones. So the output of each Hall switches alternate between high and low for every 180 degree. So it's wrong because it is becoming high and low after every 120 degrees. This option is wrong. The output signals from the Hall switches are identical except for a phase shift between each other. Output each Hall switch alternate between high and low. Yes, this is like correct option. Option A is correct here. But as we can see in graph, after every 180 degree, it will become high and low. So this is the case. This is the maximum here. And again it will become 0. Then it will be minimum. And again it will become 0. And again it will be maximum. So after every 180 degree, it will switches from high to low. So the option A is the correct option here in this case. And the output signals from the Hall switches are identical except for a phase shift between each other. This is also a correct option. Output state of a Hall switch depends not only the rotor position but also depend upon the direction of the rotation of the rotor. So this is the wrong option. And every Hall switch output completely determines the active zone of switches in one respective length. So this is also wrong. So option A and B is correct for this question. And option C and D is wrong. So but in this question it is asking wrong. So option C and D will be the correct. So now we'll solve a numerical question, that is a rotor of a brushless DC motor rotate as a speed of omega is equal to 1200 rotation per minute. So the rotor of the brushless DC has four poles. So there is four poles, two north pole and two south pole. So the frequency of the output pulses from each Hall effect switch is. So in this question we have to ask the frequency. So we all know that speed is equal to speed of rotation is equal to 120 into frequency by pole. So this is the formula. So using this formula, we have to find frequency, that will be speed of rotation, P into speed of rotation divided by 120. So it will become 4 into 1200 by 120. So this will be 40 hertz. So for this question, the answer will be 40 hertz. Now moving on to the next question. When the operating speed of a brushless DC motor decreases, the frequency of the torque ripple. So the frequency of the torque ripple depends upon the speed of the rotation, and also the torque depends upon the speed. So the operating speed decreases. So therefore torque will also decrease. So for this question, and it is proportional to speed, so it is decreases in the proportional to the speed. So move on to the question number 9. In comparison to a forward rotation in the In comparison to the forward rotation, in the reverse rotation operation of a BLDC motor, so the polarity will change as compared to the forward rotation in the reverse rotation. So the correct option is the magnitude of an induced EMF remains same, but the polarity is different for a given speed and range of rotor angles. Moving on to the 10th question, that is the switching logic for operating the inverter switches in a BLDC motor drive cannot be employed in PMSM through the inverter topology remains the same. This is because so PMSM is permanent magnet synchronous motor. So PMSM requires the sinusoidal current flow, and this BLDC requires the DC current, and it should conduct in each phase. So the correct option is option D, that is PMSM operation necessities is a sinusoidal current follow, while BLDC demands a DC current while each phase conducts. So now we will solve some of the numerical questions. In this question, it is given if the ratio of the flat intervals of the back EMF of a two-pole brushless DC motor at two different operating speeds at a given load is 2:1 at a steady state. Determine the corresponding ratio of the fundamental frequencies of their respective ripple torques. So we have to find the ratio. So the ripple in the torque occurs at a rate which communication occurs, and this rate is a function of the operating speed. So occurs at a rate is a function of the operating speed. So the ratio of the frequencies of ripple torque is thus the same as the ratio of the respective speed. So ratio of the frequency of ripple torque is thus the same as the ratio of the respective speeds. So the ratio will be same, and the ratio of the frequency of ripple torques will be 2:1 only. So this ratio can be represented as a 2. Will be same as 2:1. So move on to the next question. So the rotor of a four-pole brushless DC motor rotates at 600 rotation per minute. Determine the duration of high pulse interval for the output of any of the Hall switches. So we have to determine the high pulse interval for the output of any one of the Hall switches. So in this, the speed of the motor omega is given, that is 600 rotation per minute. Therefore, time taken for 1 revolution time taken is equal to 60 second by 600 rotation per minute. So this will be 0.1 second. Okay. Since the number of poles is 4, here pole is number of pole is 4. So one mechanical revolution is equivalent to two electrical cycles. Two electrical cycles. So duration of one electrical cycle is equal to 0.1 divided by 2, that is equal to 0.05 seconds. So now the Hall switch output remains high during 180 degree of an electrical cycle. So during one cycle, Hall switch remains high for 180 degree. So that is a half of the time, half of the time duration, okay, for one cycle. So high pulse interval is equal to 0.05 divided by 2, that is equal to 0.025 second. So for this question, 0.025 second is the correct answer. So the duration of high pulse interval for the output of any of the Hall switches is 0.025 second. So the next question is, for the determination of a speed of a two-pole brushless DC motor, a student made use of the Hall switch outputs. He was measuring the time duration taken between two adjacent pulse transitions occurring among the three Hall switch outputs. During a certain operating condition of the motor, he observed that the time interval is 0.0125 seconds. Determine the approximate speed of the motor in that case. So the two adjacent pulse transition of the Hall switch outputs occur at an interval of 60 degrees. So two adjacent pulse transition of Hall switch occurs at interval of 60 degrees. In this question, it is given that the duration is 0.125 seconds. So duration for 60-degree interval is given as 0.0125 second in this question. It is given here. So the machine have the two pole here. So in two pole, one mechanical revolution is equal to the electrical revolution. So electrical angle is equal to mechanical angle. So for 60-degree mechanical rotation, it takes 0.0125 seconds. So time for one revolution is equal to 0.0125 divided by 60 into 360 degree. So it will become 6, so it will become 125 into 6. It will become 0.075 seconds. So the speed is equal to, this is for per revolution. So that is equal to 1 by 0.075 revolution per second. So this will become 1000 by 75. It will become 13.33 rotation per second. So if we multiply it with 60, so rotation per minute will be equal to 40 by 3 into 60. So it will become 800 rotation per minute. So for this question, the approximate speed of the motor omega is equal to 800 rotation per minute. So we'll solve the last question for today. So consider two-pole PMSM motor. If the motor is desired to be run at 1500 rotation per minute, what would be the frequency of the frequency in hertz of the voltage that needs to be supplied from the inverter? So we know that the frequency formula F is equal to P into N by 120. P is the number of poles and N is the speed in the rotation. So here we can write omega also. So omega is equal to 1500 rotation per minute. So in this one we have to find F. So P is equal to 2 given. So 2 into 1500 divided by 120. So it will become 25 hertz. So the frequency of the voltage will be 25 hertz. So I will close the lecture here only today. So this slide and the video will be uploaded on the YouTube, and slide will be uploaded on Google Slides. So from there you can watch this lecture if you have missed now. And if you have any doubt, then you can ask in the comment section also. So after week 8, the domain will be little more uh, related to my part, so I will explore it more, and I will give more question after the week 9. Okay, thank you everyone for attending today's lecture. So we'll close the lecture here on. Thank you.